Welcome to the Explainer. Today, we're going to pull back the curtain on the hidden engine that powers pretty much every search you've ever done. It's a 50-year-old idea you've probably never heard of called the B+Tree, and it's the quiet hero that makes our digital world feel so unbelievably fast. Every single day, we create an absolutely mind-boggling amount of data. We're talking something like 2.5 quintillion bytes. To put that in perspective, that's a 25 with, get this, 17 zeros after it.
So that brings up a huge question, right? How in the world do our databases and file systems dig through billions, even trillions of records to find that one thing we're looking for and do it in the blink of an eye?
Well, the secret isn't just about raw computing power. It's actually a super elegant solution that was cooked up over 50 years ago, specifically to deal with the physical slowness of old-school spinning hard drives.
Okay, so to really appreciate just how genius the B+Tree is, we first have to understand the problem it was built to solve. And it's a physical problem, one that's rooted in the way computer storage actually works.
So look at it this way. Grabbing data from your computer's memory, that's lightning fast. We're talking nanoseconds. But reading from a physical disk drive is thousands of times slower. It takes milliseconds because a little physical arm has to literally move across a spinning platter to find the right data. That delay is called seek time.
And that analogy is just perfect. Every single disk read is a huge time penalty. It's like having to get in your car and drive to a massive library just to look at a single page. So the whole game becomes, how do you make as few trips as possible?
So facing this massive bottleneck, two researchers over at Boeing came up with an absolutely brilliant solution way back in 1970.
Their names were Rudolf Bayer and Edward McCreight. And their goal was pretty straightforward. They needed to design a data structure that could organize these giant indexes on a disk, but, and this is the crucial part, require the absolute minimum number of those agonizingly slow disk reads to find anything.
So what does the B actually stand for? Well, the funny thing is, the inventors never really said. It could be for Boeing, where they worked, or maybe balanced, which is a key feature of the tree, or maybe even for Bayer, one of the inventors. As McCreight's quote kind of hints, the mystery is part of its charm.
Okay, so how exactly does this thing work? How does it achieve this incredible efficiency? Well, it all comes down to its unique shape and structure.
You see, a B-tree is a self-balancing tree. But unlike a simple binary tree where each little piece or node can have at most 2 children, a B-tree is short and fat. A single node can have hundreds, maybe even thousands of children. This makes the tree incredibly wide and bushy, not tall and skinny.
And that right there is the secret sauce. Each level you have to go down in the tree, that's one disk read, one trip to the library. So by making the tree incredibly wide, its height stays incredibly low. You could have a B-tree indexing millions of items that's only 3 or 4 levels deep. That means finding any single thing takes, at most, just 4 of those slow, expensive trips to the disk.
But that raises a big question, right? How does it stay so short and balanced when you're always adding new data? What happens when one of those nodes, one of those chunks of data on the disk, gets completely full?
And this is where the magic really is. Instead of just adding a new level and making the whole tree taller, which would slow things down, it does something way smarter. It splits that full node right down the middle, it finds the median value and promotes it or pushes it up into the parent node above it.
The result? You get 2 new nodes, each about half full, with plenty of room for more data. This clever balancing act is always happening, and it makes sure the tree grows wide, not tall. That is the key to keeping it so fast.
Now, the story doesn't quite stop there. In the real world, most modern systems use an even more effective version called the B+Tree.
The most important difference between them is where the actual data is stored. In a classic B-tree, your data values could be in any node. But in a B+Tree, all the real data, or at least pointers to it, live only in the leaf nodes, the ones at the very bottom level. And this gives it a huge advantage, much faster searching and especially faster range scans. This one little change has a massive impact. It basically turns all the inner nodes into pure directories. They don't hold any actual data, they're just filled with keys that act like signposts, pointing the search in the right direction. All the valuable stuff lives in the leaf nodes, which are also linked together like a chain, making it incredibly fast to just scan through a whole range of data.
So you end up with two really specialized kinds of nodes. You've got these slimmed down inner nodes that are just traffic cops, which lets you pack more of them into a single disk read. And then you have the leaf nodes at the bottom that hold all the actual prizes.
You know, this might seem like a really deep, abstract computer science topic, but B-trees and their variants are truly the unsung heroes of our modern digital world.
Seriously, where are they? Everywhere. They're the indexing backbone for basically every relational database you've ever heard of. They're in the file system on your computer, whether you use Windows, a Mac, or Linux. They organize data in your phone, in your browser. They are, quite simply, everywhere you look.
So the next time you hit search and get a result back in just a fraction of a second, you'll know to think this elegant 50-year-old data structure. And it kind of makes you wonder, doesn't it? What other fundamental decades-old ideas are out there, just quietly running our world?